Hi everyone, my name is Tianyi, and I work with Jingjie on a ECE-561 project. Our project name is Automatic Guided Vehicle. It is a self-balancing and object tracking robot. So we want to design an embedded system that help us understand how embedded system interact with the outside world. The system should be able to adjust itself with feedback information, and we hope the system that can make people's life easier. Then we found this very interesting topic has been developed during the late 20th century. Automated guided vehicle. It's a mobile robot used for transportation, basically in the industry, such as the manufacturing line. As you can see in the picture here, it can carry the stuff by itself. But it has not been implemented a lot to people's daily life. There has been some usage, like in the hospital, they will be carrying patients and stuff. But we're trying to find something like pretty closely related to people's life. We come up with this idea of automated luggage, that luggage will following people, that this vehicle can help people carrying the luggage. So that's basically our motivation. About the contributions, I work on the circuit board design, hardware part, and Jingjie work on the software part, the OpenCV and Arduino coding. And we both came up with the idea of homemade cardboard vehicle frame, which I'm going to talk about in 2 slides. So about the components requirements, the first requirement we have is to track identified object or person by a sensor, which has been done by the Raspberry Pi with a camera module that can help us locate the object and identify it so that we can send out any instructions to the vehicle. And we consider it as a master board. And then the self-balancing requirement is achieved by having the Arduino Uno with the GY80 multi-sensor board, and the accelerometer and the gyroscope helps to calculating the angle of balancing, which helps control the motor to achieve the balancing option. So the Arduino board is gonna do the balancing as a slave board, which also consider the fact that Uno is super easy to interact with all the sensors. We think it's a very good idea to split the load. And then we want the vehicle frame to be robust and low cost. And so we come up with this handcrafted, made of cardboard design. We have 2 prototypes of that, which I'm gonna go over that in the next slide. And a motor controller, which will allow us to have fast response to balancing angle. We decided to pick the AL289 and dual bridge motor driver. It's a very commonly used motor driver and very easy to interact with Arduino with some elaborate exister. Motor speed is going to come controlled by the PWM. Here comes our structure design. I'm very proud of this design, came up by ourselves. It's a cardboard, basically shipping box cardboard. We folded it and we add the plastic layer in the middle to just make it stronger, and wrapped up with the boxing tape to secure it and protect the cardboard with any outside world damage like liquid. It is basically a box, as you can see there in the pic, holding the boards and the cables. It has a very low center of gravity, which the vehicle gonna swing at a very high frequency and hard to balance itself. We tried a couple of times with our code, but we still have this problem. And the boards and the cables does not have extra room between them, so that might cause shorts between circuits, and because we don't have lots of space inside the box that holding it, as you can see, all the IOs on the boards are very hard to reach, which makes it really hard for us to debug the code. So we have an improved vehicle structure, as you can see later in 1 second in the next slide. We have a pushing module here, a pushing module, as you can see in the pic. It has a thickness enhanced double side board. Basically, we put 2 grooves inside the original design, so that you can push the module inside it, and then on this module you can lay out all the boards, like the motor driver, Arduino, and your Raspberry Pi on it, and then all the cables are connected to the bottom, like the plus and minus. There's a breadboard there. Other connections are just made between the boards. As you can see, it's a pretty clear layout compared to the last version, which I really like it. And then the I/O, like the USB, is at the top. Very easy, also very easy for us to debug the code.
As for the software part, first we are going to talk about the code that is running on the Arduino board. We initialized all the pins, sensors, and communications in the code, and we used a library. It is called LF library, which is really useful. There's one thing that is important: the sensitivity of the gyroscope. When the sensitivity of the gyroscope is high, like 70, the robot will respond much slower. And when the sensitivity of the gyroscope is low, like 17.5, the value of degree per second will be at 500, and the robot will respond much faster. Choosing the right value of sensitivity is important. In our project, we set the value at 70, as we know that all of the sensors have deviations and noises, so it is required for the robot to use a math filter in order to reduce deviation and noise by merging the signals returned by the sensors. In our project, we had two alternatives, and finally we chose the complementary filter because it performed much better on reducing delays. The Arduino board is able to read digital signals from Raspberry Pi so that we can use it to control the motion of the robot. Even we had finished programming, we still had to test the robot in the real world since the PID value had to be turned. The PID is widely used since it is able to help maintaining the process set point. When we have different gyroscope sensitivities, we need to use different PID values, even for the same robot. We used a simple approach to turn the PID values. We started from KP, then KD, and finally we turned KI. The law of the PID tuning is that we shouldn't make the system perform oscillation, and we need to be patient since it can always take a long time. In our project, the final configuration of PID is 90, 2, and 0, where the sensitivity of gyroscope is 70. With regards to the object tracking function, we use the OpenCV running on Raspberry Pi. As you can see in the first picture, we can select the region of interest just by clicking the left button 4 times on the mouse. And it's also able to estimate the distance between object and the camera by evaluating the size of minimal enclosing circle for the tracking rectangle. We can use GPIO pins to output digital signals to the Arduino board and control the robot to stay on position or move towards the identified object.
So here comes the conclusion and some future work we would like to do. So we think it's a very practical model for the AGV being implemented in this real life situation, as the carrying the luggage for people. And then we think it's a very good combination of software and hardware. We learned how to use OpenCV and some Arduino programming, like also the Arduino sensor like accelerometer and gyroscope, and the motor driver, of course, very fun to play around with it. Also the DC motor adjusting the speed. Sometimes improvements can be achieved besides the hardware and software now, like the board, like the pushing module, the vehicle frame design we came up with. We need to think broadly. We could implement it better hardware or optimize the software to make the vehicle react more quickly to the change of angles. Basically, will enhance the balancing performance. We could use a Raspberry Pi 2, which is faster processing speed and bigger RAM. Also, a servo motor will help to control the angle more precisely. Also, we can optimize the OpenCV code, which will make it faster. That's it. Thank you.